Just think about it for a second. Your phone, your laptop, the lights in your room, they're all using it right now. We're talking about electrical power. It's this invisible force that pretty much drives our entire modern world. And today, we are going to figure out exactly what it is. Seriously, have you ever stopped to wonder about this? I mean, they both plug into the exact same wall socket, right? But one of them can make your electricity bill shoot through the roof, while the other costs practically nothing to run. It just doesn't seem to add up. So what on earth is going on here? Well, the solution to this whole appliance mystery, it isn't magic, it's just pure physics. And it all comes down to understanding one single fundamental concept: electrical power. Okay, let's look at our main suspects: a kettle and a phone charger. In the world of electricity, one of these is an absolute power-hungry beast, and the other is just a gentle sipper. The real question we need to answer is why? So, to really crack this mystery, we've got to get to the very heart of this key idea. Because I promise you, once you understand what electrical power really is, the way every single appliance in your house works will suddenly just click into place. So here it is, the big definition. Power is all about speed. It's not about how much total energy an appliance uses over its lifetime, but about how quickly it's moving that energy right now. Think of it like the flow rate of energy. And this is a brilliant way to think about it. You know, a world-class sprinter uses a massive amount of energy, but all in just a few seconds. A casual walker, on the other hand, uses energy way more slowly. While high-power appliances, they're the sprinters of the electrical world. And here is where the difference becomes just mind-blowing. I mean, look at these numbers. A typical kettle is rated at 3,000 watts. Your phone charger, a teeny tiny 5 watts. Get this, that means the kettle is transferring energy 600 times faster. No wonder it has a bigger impact on your bill. So what does that unit, the watt, actually mean? Well, it's the bridge that connects power to energy. 1 watt is just a transfer rate of 1 joule of energy for every single second that goes by. So that 3,000 watt kettle, it's burning through 3,000 joules of energy every single second it's switched on. Okay, concept down. Now let's open up the toolkit that you're going to need to actually calculate all this stuff. For anyone studying GCSE physics, trust me, these formulas are about to become your new best friends. You know how in every toolkit there's that one essential go-to screwdriver or wrench you use more than anything else? Well, for electrical power, that multi-purpose tool is one beautifully simple and incredibly important equation. And here it is, P equals I times V. That's power equals current, which is the flow of electricity, multiplied by the voltage, which you can think of as the electrical push from the socket. This is the big one, folks. You absolutely have to know this. It's the fundamental link between all three, and it will come up again and again. Okay, for those of you aiming for those top grades on the higher tier paper, we need to add a couple more specialized tools to the kit. Now, they both come from P equals IV, but they are super useful in certain situations. First up, we've got power equals current squared times resistance. This formula is fantastic when you get questions about power that's lost as heat in things like wires or resistors, because it directly links power to resistance. And the second advanced tool is power equals voltage squared divided by resistance. This one is perfect for those moments where you know the voltage and the resistance of something, and you need to find the power without even knowing what the current is. It's a great shortcut. All right, enough theory. Let's take these formulas off the page and see how they actually apply in the real world, to the stuff in your home, and more importantly, to the questions that pop up in your exams. So the power ratings of stuff around your house vary a lot. We go from just 5 watts for a phone charger up to a pretty hefty 1,000 watts for a microwave, and then all the way up to a colossal 9,000 watts for an electric shower. This is the physics behind why a hot shower costs so much more than charging your laptop. Next time you plug something in, have a look. You'll probably find this power rating printed right on it. Right, let's put our knowledge to the test. Here's a typical exam question. You're told a kettle transfers 600,000 joules of energy in 200 seconds, and the question is simple: what's its power? So, how do we tackle this? We're going to solve this in 3 easy steps. First, pick the right tool for the job. We have energy, E, and time, T, so we're going to use a core power formula. Power equals energy divided by time. Step 2, we just plug in our numbers. And step 3, do the math. 600,000 joules divided by 200 seconds gives us 3,000 watts. And hey, that's a perfect match for a typical kettle. See? Simple. Okay, knowing the formulas is one thing, but avoiding the common traps that catch people out in an exam, well, that's what separates a good student from a great one. So let's go over a few pro tips to make sure you don't lose any easy marks. So here are the big things to watch out for. First, please never ever confuse power in watts with energy in joules. They are related, but they are not the same thing. Second, always watch out for kilowatts, or kW. If you see it, you probably need to convert it to watts by multiplying by 1,000. Third, if a question mentions a rate per second, that is a huge clue that you need to be dividing by time. And finally, just take a breath and pick the right formula from your toolkit for the information you've actually been given. All right, let's do one final power up and lock in the absolute key points from all this. If you remember nothing else from this explainer, remember these things. Here we go. 1. Power is the rate of energy transfer, how fast energy is used, and it's measured in watts. 2. P equals I times V is your number one must-know formula. 3. You can literally find the power rating on almost any appliance you own. And 4, the bottom line is higher power means faster energy use, which means it costs you more money. And that leaves us with one last really crucial thought. We now understand power, which is the rate of energy use, how fast you're using it per second. But your electricity bill isn't based on that, is it? It's based on the total amount of energy you use over a whole month. So how do we connect the two? How do we get from those instantaneous watts to the total energy you're actually charged for? Well, that's the next big piece of the puzzle. Hope this helped you understand the power all around you.